Okay, this news.
Oh.
Breaking news. 5 people died this morning because of overloaded boat. Let's the video.
Yay! This is so fun! OMG! Can I join you guys?
No, you can't. Maximum capacity is only 4 people.
I don't care. Wait! It's gonna sing! Ah!
Why does the boat sing? Let's find out.
Alright, firstly, we have to understand how does a boat floats, which is explained by buoyancy. As what have been stated in Archimedes' principle, the upward buoyant force exerted on a body immersed in a fluid, whether partially or fully submerged, which arises from hydrostatic pressure acting on the submerged surfaces of the body. This buoyant force is equal to the weight of the fluid displaced by the body and acts vertically upward through the center of buoyancy, or we labeled it as B. So, we can say that a boat floats because its weight is balanced by the buoyant force. And if the weight of the boat is greater than the buoyant force, the object will sink. And another important element for a boat is to have a stability. It is essential for it to return to its original position even after being tilted by external forces such as wind or waves. When a boat is tilted, the hydrostatic pressure forces acting on the submerged area is asymmetrically distributed due to different depths on different sides. Hence, it causes the center of buoyancy to shift laterally. So, to achieve the optimum stability, the metacenter should be located higher than the center of gravity. When this condition is achieved, a righting moment is produced, which is sending the boat to its original position.
The boat materials. The materials that we use to make our boats is popsicle stick, the stick used to make the main body of the boat. Next, the water bottle. The bottle is placed underneath the boat as a support and to provide the buoyancy for the boat. Next, plastic sheet. Plastic sheet is placed underneath the popsicle stick to avoid the stick to expand when it's wet. According to Archimedes' principle, the buoyant force acting on a floating body is equal to the weight of the fluid displaced. This is expressed by the buoyancy force equation Fb equals to rho gv. For the boat, floating equilibrium occurs when the buoyant force equals to the total weight of the boat. The weight of the boat can be calculated from the formula W equals to gamma times V, where the gamma is the specific weight of the boat and the V is the volume of water submerged. So when the W is equal to the buoyant force, the boats float with a constant depth of immersion in the water. The depth of immersion is calculated from the formula X equals to V over A, where A is the plane area of the boat. The depth of immersion of our boat is 0.011 meter. By this information, we can get the center of buoyancy of our boat. The center of buoyancy is the geometric center of the volume of fluid displaced by the floating boat, where it represents the point where the upward buoyant force acts, where in our case we assume that the center of buoyant is placed 2/3 from the base of our boat because the base shape of our boat is a circle where the immersed area of the boat is less than a half circle. When the boat carries no loads, its weight is small, so only a small volume of water needs to be displaced. The body floats high on the water with a shallow draft. The buoyant force acts through the center of buoyancy, which is the centroid of the submerged volume, while the weight acts through the center of gravity, located near the geometric center, so the system of the boat is stable. When a load is added, the total weight increases. To maintain equilibrium, the boat sinks deeper, increasing the displaced volume and therefore the buoyant force. At the same time, the center of buoyancy moves outward because more of the hull is submerged, while the center of gravity shifts towards the added load. This behavior is exactly the same for a boat carrying cargo. Stability is assessed using the concept of the metacenter. When the floating body is slightly tilted by waves or disturbance, the submerged shape changes, causing the center of buoyancy to move sideways. The intersection of the buoyant force line with the original vertical axis defines the metacenter. The distance between the center of buoyancy and the metacenter is called the metacentric radius, given by mb equals to I over v, where I is the second moment of inertia. The overall stability is described by the metacentric height, given by ymc equals to mb plus ycb, where the boat will be stable when the ymc is greater than ycg.
What will happen when 2 Newton load is on the boat? From the video, when the 2 Newton load is placed on the boat, the total weight of the boat increases slightly. The boat displaces a small amount of water. The buoyant force balances the weight. The boat floats higher in the water and the center of gravity remains low. The result is the boat is stable with good balance and minimal tilting. What will happen when 6 Newton load is on the boat? From the video, when the 6 Newton load is placed on the boat, the total weight becomes significantly higher. The boat must displace more water to generate enough buoyant force. The boat sinks deeper into the water and the center of gravity rises. The result is the boat is less stable compared to the 2 Newton load and is more likely to tilt.
What happened when the load exceeds the boat capacity? Let's see the video for example. As you can see, when we put the 10 Newton load, the boat can't stay floating due to the exceed load. So, by here, we need to know why the boat can stay floating. So, to know that, let's see the diagram. When the load at the range of boat capacity, YMC greater than YCG, but at 10 Newton, the YCG is greater than YMC that make the boat unstable. When the 10 Newton load is applied to the boat, the total weight of the system exceeds the maximum buoyant capacity of the boat. As a result, the boat is forced to submerge deeper in order to displace more water. However, at this stage, the boat is no longer able to displace a sufficient volume of water to produce an upward buoyant force equal to its weight. This means the buoyant force becomes smaller than the total weight, causing the boat to continue sinking. At the same time, the additional load causes the center of the gravity to shift upward, increasing the instability of the boat. Although the center of buoyancy shifts slightly due to the increases submerged in insufficient contract, the increases weight. Consequently, the metacenter falls below the center of the gravity, resulting in negative metacentric height. Instead of producing a right moment, the overturning moment add on the boat. This prevents the boat from returning to the original position when disturbed. Due to the combined effect of excessive weight, insufficient buoyant force, and loss of stability, the boat becomes unstable and eventually sink completely when subjected to 10 Newton load.
In summary, this experiment helps us understand how an empty bottle floats on water and what makes it stable. First, the bottle does not go fully underwater. Only part of the round shape of the bottle is submerged. This allows the bottle to push water away and stay floating. The bottle floats because of buoyancy. Buoyancy is the upward force from water. According to the principle of buoyancy, the upward force is equal to the weight of the water that is displaced by the bottle. When this upward force is equal to the weight of the bottle floats. The position of the bottle in water also depends on the center of buoyancy. This is the point where the buoyant force acts, and it is located at the center of the submerged part of the bottle. Another important factor is the center of gravity, which is the point where the weight of the bottle acts. For the bottle to stay stable, the center of gravity must be in suitable position. Stability is explained using the metacentric condition. If the meta-center is above the center of gravity, the bottle will return to its original position after being slightly tilted. This means the bottle is stable. Lastly, the submerged area of the bottle can be calculated using simple circular geometry. This helps us understand buoyancy and stability in an easier way without using complicated calculation. Overall, this experiment clearly shows how buoyancy, center of gravity, and stability work together to control the floating behavior of an object in water.